tedious. So let us restrict ourselves to setup, and then maybe if there's an easy one, I could do the whole thing. But setting it up is the main thing, getting it into the right thing. So were any of these that you did problematic where we need to take a look at them? Yeah, what do you think? What was that, Matthew?
7.
Number 7? Okay, let's take a look at 7 and see how that is done. This one, hopefully, when you look at that, you say, that's going to be a thing that we're going to convert to polar form. And in fact, that's what I will do. So I'll get the double integral set up for you, but then we won't do this one fully because this one would be a little bit on the tedious side, let's just say. So I'll just shove it down here. And then maybe we could find one that is rectangular that we can get set up as well. And if it's non-tedious, I could do it. But anyway, so hyperbolic paraboloid, and we're between these two cylinders. Hopefully you can see that we're dealing with this sort of a situation. So this is 1, this is 2, and we're interested in this sort of disk. If you look, or the annulus, sorry. If you're looking down on whatever this is from above, you're going to see probably a little bit more regular of a circle. I was lazy and just did that. But anyway, it'll look like this, a circle with a hole in it. But of course, the surface itself, this thing is this hyperbolic paraboloid, saddlose is what it is. It's going to be more like a Pringles potato chip with a hole drilled out of the middle of it. Maybe you could think of it that way. And we want to know the surface area of this thing. So let's go to it. First things first, I'm going to just do the derivatives. dx is going to be negative 2x, and dz over dy, or the derivative of partial of z over y, is 2y. Okay, so let's set this up. Double integral, of course, over this region. So we'll deal with the whole polar coordinates in a minute. But and then we have the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared. That's the main thing to remember. If you can remember that, you're going to be fine today because the one on the quiz is in rectangular coordinates. It is a relatively simple, like when you get to this stage, it should be super easy. If it's not, you've done something wrong. But this one is not super easy. We have a little bit of work to do. So give me a sec. Let's first of all expand the stuff under the parentheses and then factor. So we have x squared plus y squared, if that's okay. So all I did there was I got 4x squared, 4y squared, and then I factored out the 4. Now we can deal with the limits and converting to polar coordinates. So over here, I will put the polar coordinates thing. The angles, of course, go from 0 to 2 pi. The radius goes from 1 to 2. And then you're going to put this function, and I'm going to do it the easy way. If you choose to do it the hard way, that's on you. But I'm just going to change x squared plus y squared to r squared, put in the extra r, and that should do it other than the actual calculation. This one is similar to the one that we did last time. And that is, you do a pretty straightforward substitution. U is equal to 1 plus 4r squared. Du is going to be 8r dr, so you're going to have a factor of 8/1/8 somewhere. But hopefully at this stage you can get from here to the finish line on this one. Did that clear things up? Okay, good. Okay, so yeah, this one actually isn't all that tedious, to be honest, but I want to see if there's a rectangular problem that we could do that you had trouble with. Maybe the rectangular ones were all too easy. Yeah, what do you got, Daniel?
For question 3, just to confirm the limits.
Yeah, so it lies in the first octant. So that one's confusing because they don't tell you what this looks like. So yeah, let's go ahead. 3, 2, 1, and 6. Just a sec. I'll just copy it down. So you have 3x plus 2y plus z is 6. So even though Daniel wants to just get the limits, let's actually, we'll use this as the example of one that is relatively simple to do, that's not as tedious. The main tedium is getting the limits. So let's draw this, what this looks like. Okay, so if x and, sorry, no, yeah, if x and y are both 0, then z is equal to 1. So this point is on this plane. When x and z are both 0, I'm just plugging this in. I think you can probably do this in your head. Put x and z equal to 0, you get y equals 3. That point is also in this plane, 0, 3, 0, and then one more point. You can probably guess it's going to be 2, 0, 0, and that's when y and z are both 0. So if you can imagine those 3 points on those 3 axes and then connect them with the lines, you get a plane. That plane is the plane that we're interested in. And in fact, the portion of the plane that happens to be represented by that triangle is the actual surface. That's what we're interested in. It's the surface area of this triangle. So basically just the area of that triangle is what we're going to end up with. So, so let's get the limits. Imagine taking this thing and turning it so that the z-axis is pointing towards you, y-axis is pointing up, and looking down on this thing. Here's what it's going to look like. We have this point here. Since I'm just going to put the x and the y-axes on this thing, I'll just write it in 2 coordinates instead of 3. So looking down at the xy plane, z is pointing out towards you. This point is that point. And then the 0, 3, 0 ends up appearing to be up here at the point 0, 3. So we have this nice triangular region. Now finally, I'll get to your limits, Daniel. This, by the way, is y is equal to, what is it going to be, 3 minus 2/3. Just a minute. 3 halves. 3 halves. Had to take a minute there to work out the slope. So nice, relatively easy line that you can figure out without doing much work there. 3 minus 3 halves x is what we get there. Okay, so here's how I'm going to set this up. I'll use a vertical rectangle. Dx is on the outside. Okay, so we have dy, dx. The x goes from 0 to 2. So just to remind you, we have this sort of vertical line, this knife, if you will, that is cutting through this thing. And so the outer limit is always where you start and where you end. So where does it's always going to be constant. Don't give me a variable on the outside. It won't be x equals y. It's x equals 0, x equals 2. Inner integral is always, those are functions. So you're going to start at y equals 0. The function y equals 0. I know it's a constant, but it's a constant function. The upper limit for y is going to be this curve, well, straight line. 3 minus 3 halves x. So whatever curve is the up and the bottom is going to be your limits on the inner integral. If it was a horizontal rectangle, of course, and this is something that is hard, you would have the same thing, but it'd be the left and the right sort of functions. But they're always functions. So inner integral is functions, outer integral is always just constants. Let's just finish this up since we've gotten this far. But let me make sure, Daniel, that's what you asked about is the limits. You got your limits? Excellent, you got your limits, very nice. Let's just finish this though, because this one's pretty straightforward. 1 plus the derivative in the x direction. So I'll just write this, let's see, take this and rewrite it like this. Z is 6 minus 3x minus 2y. So partial of z with respect to x is negative 3. Partial of z with respect to y is negative 2. So let's stick those in there. Negative 3 squared is 9. Negative 2 squared is 4. So I'm left with that. And what could be easier than a nice constant integrand? It would be nice if the limits were constants as well, but they aren't. So there it is. So now the rest of this I think we can do, but I might as well finish it up since this is so easy. I'll get the integral from 0 to 2 of radical 14 times 3 minus 3 halves x I know I just skipped 2 steps there, but if, please do, it's going to be, well, here, I'll write it down. I'm doing a disservice to you. My apologies. Here. There. It's not that hard, is it? If I want you to do it, I guess I have to do it. There. Okay, so there's the inner integral. That you take this, integrate with respect to y, and you just put a y there, and then you're going to plug in those limits, and you get that. So what's the big deal, right? And then we'll do the outer integral. So let's see, radical 14, 3 radical 14 times x, that's this stuff, minus 3 radical 14 over 4 times x squared, that's that stuff, the 3 halves x times the radical 14. So integrate, you get x squared over 2, so you have another 2 down there. Evaluated from 0 to 2. And let's see, what do we get here? This will be 6 radical, let me get rid of all that, it's messy. Try again. 6 radical 14, that's when you plug 2 into all of that stuff. This is supposed to be a 2. And then x squared is 4, so 3 radical 14 minus 0, so 3 radical 14. There we go. Very nice. So it ends up being relatively easy, relatively nice. One on the quiz is similarly easy, I think, at least for the calculations. Just have to get it set up. Integral, radical, 1 plus the derivative in the x direction, squared, derivative in the y direction, squared. All right, everyone's ready. You're saying, let's get it done. We got to go get our physics done. That's more important, right? Okay, here, 1, 2, 3, 4. Here you go. Enjoy. 1, 2, 3. There you are. 1, 2, 3, 4. I think there's more there. No. Oh, there's 5 here. Oh, we don't even need. Oh, well. Here, you can have that. Send that here. This one here. This one here. And then there's one for the blank person. He's going to show up like right here. You need one? Hold on. Pile. Alright, I guess I better put this up on the screen too. Surface area. There it is. hopefully you're coming down the home stretch with this. Wasn't too bad, was it? I guess that if you got it right, it probably wasn't too bad. If you got some nasty decimal that involved pi, you're probably not right. Or radical 103. Very nice so far. Good job. Well done. That's good. Sure. That's fine. Is that your own graph paper you're making there? Very nice. So, you're happy with this? I guess he's not happy. Very good. Good job. Meditating over here. Hey, Steve, I want you to stop meditating. Yes, I want you to stop. It looks great. Okay, almost done. You're finishing it up. Good job. You're going to finish it up here in just a sec. Good job. Kind of open. Kind of open. Very nice. Good job. Oh, you're so close. Okay, good. All right. Got something? All right. You're really close. Trust me. Here. Okay, let's take a look and see what this looks like. Let me staple these. Oh, you got one? Oh, okay. You're all done?
No, not all done.
Oh, you're almost done.
Just give me a second.
Okay. Yeah. Okay. So if that was a good integral for you,
Yeah.
put a box around it.
I'll just.
Yeah. Okay. Good. Sorry to rush you, but we'll get these physicists out of here. Oops. Oh well. All right. You get to see the answer. All right. So where's my answer? Do I want it? There it is. Yeah, I apologize for the graph wasn't as good as I because here we go. I think I changed my my function after making the graph, and then I was like, wait a minute, it'll be better if it turns out. Oh, you can see the answer over there. Oh well. So 0, 0. So I had to count by twos, 2, 4, 6, and then 2, 4. So you have something like this. I don't know. Oh no, that's not it either. Let me undo. Here, sorry about that. No, it's just because I'm rushing. There, is that better? So you've got those 3 points, very nice. And so, but the important thing, this is y equals 2x right here, so my double integral is going to look something like this. Y goes from 0 to y equals 2x, x goes from 0 to 3, and then in here you've got 1 plus the derivative of that. The derivative of that is 4, plus the derivative of that. The derivative with respect to y is 8. So there it is in all of its glory. But so you end up with, that ends up equaling 81. So that's why I was messing with the functions. And so this is 9. And then you do the integral from 0 to 2x of 9 dy, nice constant. So you end up with 18x. And then, so I kind of left off a bunch of steps here, but the final answer was 81, which there were a lot of 81s there. And if you didn't get 81, it was either that you messed something up here or messed up, I don't know. I'll find it. I'll do my best. But hopefully you see how this shakes out. It's pretty straightforward. I'll try to make sure it's just as straightforward on Friday when you have the test. I'm really working, and we'll talk about that more tomorrow. In fact, actually just in a few minutes probably. For now, though, we do have a little something to do. It's really not that hard because all this is it's like you've done double integrals. Well, you could do triple integrals or quadruple integrals or whatever. You just throw another integral in there, right? Once you get past 2, it's like having children. If you can handle 2 kids, you can handle 3, 4. Actually, I think 3 is the threshold. If you can handle 3, you can handle any number. But anyway, getting back to this, let's go ahead and do a few of these. There's all of them at once, so let me take these and put them on a different page. Give me a sec. Copy and delete. But basically, you know how to do this already, so it's not that hard. And I'll demonstrate this right now with this first one. Let's see, can I crop that down? I only want to see the first one. Yes, that's better. Whoops. Try again. Crop. Crop. Done. Okay, yeah, so the first one, I know it looks really crazy there, but if you just pay attention to what's going on with each of the integrals, you're going to be okay. It might have helped if I had labeled these. So notice that these numbers are values for x because of the dx. These are values of y, and then these are values of z. So as long as you pay attention to which level or which of the integrals you're doing, you can separate these and do these one at a time, keeping track of what's what. So let's do that inner integral. Not hard. X squared, with respect to x, the y and the z are both treated as if they're constants. So x cubed over 3. Just leave the y and the z alone. Don't mess with them. They're your friends. You don't want to mess. There it is. X equals 1 to x equals 1 there. So that's the innermost integral. You can just deal with that and ignore the rest for now. Plug in your limits, and you should get 2/3 as your final answer, 2/3 times y squared times z squared. Just be careful. And as you probably have figured out with the double integrals, there's a lot of opportunities for mistakes, aren't there? And here you have 3 opportunities for mistakes. And if you make a mistake on the first integral, it's all over like snowballs. So I'm not a big fan of these, but they are useful. And so we have to go over them for that reason. Just for the fact that you're like, oh yeah, I can deal with this if you have it in your engineering class or whatever. You're like, okay, you can handle it. It's not going to be a problem. Okay, but anyway, that's the innermost integral. Now let's pull down that next level. The next level is the integral from -1 to 1 dy. So notice what I've got here is dy. So we can do this now. So I'm just going to do one level at a time. And as long as I keep track and I'm careful, I'm going to be okay. So this is going to be, you're going to be required to actually be super careful. So 2/3 times y squared over, or y cubed, look at that, I just said be careful, and I blew it, y cubed over 3 z squared. So now I'm dealing with y, and then I can deal with this one, so this is going to be 2/3 times 2/3 times z squared. So technically that is 4/3 z squared. But now I have to bring down that outermost integral. And, 4/9, thank you. See, apparently, look at that. I would have messed up. So let's bring down that final outer integral. And technically, I probably should have been writing these all along. So here, just to show you what I mean by this, I've got these integrals here. Oh, I guess there's only one more integral on that level, but technically I should be writing it on each level. So we have this integral dz. There it is. Yeah, this integral dz. So it's just nice though to declutter and just focus on that innermost and then the second level. Now finally the outermost integral. So here I think you probably know what the answer is already, but let's just pound through anyway. Z cubed over 3 evaluated from z equals -1 to 1. And so that ends up being 4/9, I'll be more careful, times 2/3, which is 8/27. So I know I did skip a few steps here, specifically when you're plugging in your limits. Remember, plug in the upper limit, you get 1/3 times this stuff. And then the lower limit, you're going to subtract off -1/3 times this stuff. but 1/3 minus negative 1/3 is 2/3. So not too much of a stretch. So what do you think? Does it look okay? I mean, it's a lot more work, more busyness, but you could do it if we set aside a good 10, 15 minutes, right? Actually, this one didn't take that long. Let's do another one just to see how this shakes out. So this one I'll let you do more than me. Let's see. So this one is slightly more complicated. And that slight more complication does involve more opportunity for making a mistake. So I want to point out though, oh, I made a mistake here. I see. Speaking of mistakes, this should be a Z up here. So just change that to Z. There, that's better. Okay, otherwise it doesn't make any sense. So go ahead and try to do the innermost integral, just the innermost integral, while I go and change my PowerPoint so that it fixes that minor problem. Where is it? Triple integrals. Yes. X plus Z. That's better. Just for future generations. Okay. All right, let me go update my attendance, and I will pick a rando to start this one off. Submit. Okay. Okay, let's see how we're doing here. Oh, random. Sorry. Try again. Random student. All right, Daniel. Daniel, that innermost integral, what's the antiderivative of 6xz with respect to y?
6xyz.
Very nice, yes, because 6xz is all just constant. So just multiply it by y, and you can stick the y wherever you'd like. I like the where you put it. Very nice. And this is going to be evaluated. I'll try to be super careful here. From y equals 0 to y equals x plus z. So you can see at this point, we do have a little bit of a minor complication, but it's not terrible. Let's just fix this. 0 to 1, dx dz, just so that we can keep things straight. Does that look okay so far? Okay, let's plug this in. So 0 to 1, a lot of writing, lots of integral symbols. Just show your roommate or your special friend and they'll be really impressed. Okay, so this is going to be 6x squared z plus 6xz squared. I believe I did that right. If not, you can let me know, but double check. Looks okay. All right. All right, let's do the next level. Emily, what is the antiderivative of that thing with respect to x?
It's 2x cubed z plus 3x squared z squared.
It's almost as if whoever made this up wanted it to come out nicely. Okay, so this goes from x equals 0 to x equals z. And that someone was probably me 12 years ago. I don't know. But, okay, so that look okay so far? Let's plug those in now. And we get 2z to the 4th plus 3z to the 4th. Amazing. It always gives me joy when I find something like this, and I don't remember having done it, but I did type this up at some point in my life. I tried to figure out when. Okay, so 5z to the 4th. Beautiful. Okay, well, who gets to do this one? Let's see. Next. All right, Joshua, you know the answer here. What's the antiderivative of 5z to the 4th? Yeah, just z to the 5th. Very nice. Evaluated from z equals 0 to z equals 1. So this is just 1, isn't it? So let's hope that they work out that nicely on the test. But as we will talk, we'll talk about this a little bit more about the test in just a minute. But you'll have the answers, so you'll know. I will have quadruple checked all of the problems, because if I put an answer, I've done that in the past. I remember this happening once or twice over the past 27 years, that on this test, I'd have the wrong answer and people are like losing their minds. It's like, I don't want that. I don't want you to lose your mind. So I will be quadruple checking, especially this season of my life. I seem to be losing my mental faculties. So, making stupid mistakes. Okay, one more, and then I think I'll check the PowerPoint. We might be done. I mean, other than just a few minor things that I want to mention. So here's one more to take a look at. So this can't be that hard. Oh, wait a minute. Natural log of z. Oh, that's terrible, isn't it? Well, let's see if we can pound through. Okay, so first one is the inner integral. And notice that the inner integral is an integral with respect to y, not z. So let's just treat the natural log of z as if it were a constant, which it is. So let's see, who's the volunteer here? Just a sec. All right, not here, but I know you know how to do it. But Kelsey, you know how to do this. What's the antiderivative of the natural log of z with respect to y? So remember, it's just a constant, like the number 3.
So natural log of z times y?
Yeah, that's it. Natural log of z times y. Beautiful. So y, it goes from 0 to 1 over xz, whatever that is. dz dx. So I'm trying to be a little bit more, I should have been this careful with the first one, so my apologies. All right, let's plug this in. I know you all know how to do that. 1 to e squared. So we have natural log of z times 1 over xz minus 0. I'll put that there. Now we come to the hard part, but I think we can overcome this. I won't pick on anyone, although I think you probably all could figure this out eventually. But there's a technique you're going to use here to do this integral with respect to z. Does anyone want to just tell me what that is? What method do you want me to use? Yeah, what do you got?
Use substitution.
Yeah, let's use u substitution. What's my u going to be, Ryan?
Natural log of z.
Yeah. So probably Ryan noticed what many of you did and what I was zooming in on, and that is that the derivative of the natural log of z is 1 over z dz. And if you look closely, you'll see 1 over z times dz. So that's what we're going to do. Let me just write this again, and I'm going to do this sort of in purple, just to say here is sort of the work we're going to do. I'll set this as, do it in purple, and we'll go back to the black once we get our answer. So I'll put the 1 over x out front times the natural log of z times 1 over z dz. So this stuff, well, the inner of the two integrals that we have left, the inner integral is the same as what I've written there. All I've done is I've rearranged it. So the 1 over x is out of the way. The 1 over z is right next to the dz, so that it's super obvious that the integral is going to be 1 over x times u du. So the natural log of z becomes u. 1 over z dz is du. It just gives so much joy when things work out nicely like this. They don't always. Matthew, what's the antiderivative of u with respect to u? No, u. U squared over 2. Very good, yes. Yeah, it's you were trying to, you wanted some natural log action, didn't you? Don't worry, you can have your natural log fun on your own time. make some integrals with some natural logs. But yeah, this is simple. It's no natural logs, no exponential function here. It's just u, integral of u. It's like the integral of x, u squared over 2. All right, now I'll go back to the other color so that you can see what I've done. So 1 to 4, we have this 1 over x times the natural log of z squared over 2, evaluated from z is equal to 1, z is equal to e squared. Okay, so I know it's just kind of a lot here, but so I took that integral, it's like I got to do a substitution, did my substitution, figured out what the antiderivative was, and then notice I just put natural log in there for u, and I got back to what I'm really working on. Okay, almost there. Let's plug and chug at this point. This isn't too bad. So this is the integral from 1 to 4 of 1 over x times natural log of e squared is 2. Here, I'll write it down. I'll write it down. Here we go. Times natural log of 1. How's that? Okay, the natural log of e squared is the number 2 because natural log and the exponential function are inverses one another. And so that will be this, just a minute, 2 squared over 2. So that is, here, let's do this here. This thing, wait, why did it erase? Try again. There we go. This thing, that thing there is just this here. So 2. And then this thing over here is 0. Natural log of 1 is 0. And so I'll just write down 0 because 0 times anything is 0. And then we're left with just this. The integral from 1 to 4 of 1 over x, I guess 2 over x. Let's just make it look good. There. So that's it. Almost there. One more step. And then we'll finish things up. So Christopher, what's the antiderivative of 2 over x? I love it. 2 natural log of the absolute value of x. Beautiful. Yeah, so I was getting ready to correct. Yeah, I didn't need to. But yeah, so most of us, especially since when you're plugging in positive numbers, you're like, it's just the natural log of x. Technically, though, natural log of the absolute value of x. So you would be forgiven, though, if you just put natural log of x here instead of the absolute value of x. But just bear in mind, in case there are negative numbers in your integrand or integral, you might want to use absolute value. Okay, we're almost there. We have 2 times the natural log of 4 minus 2 times the natural log of 1. As we mentioned just a minute ago, natural log of 1 is 0. Natural log of 4, you could write that in 2 different ways. 2 natural log of 2, or you could, so in other words, you could do this, or you could do this, natural log of 8. Oh, no, 16, sorry. Ignore that for a sec, 16 there. Because the rule is that when you have an multiplying a number times a natural log, it can be 2, you make it an exponent, so it's 4 squared. Or I could have taken the 4 and said 4 is 2 squared and pulled the 2, the exponent out from. So either one of those, or this, they're all 3 the same thing. But if you're cool, you'll pick one of those. Probably this one, 4 natural log of 2, I think is cooler than natural log of 16. But either one, any one of those works. Okay, why? Why do we do this? Well, we've done centers of mass for laminas, and I mentioned sort of waving my hand, and I'm going to continue to wave my hand, that you could do the same thing in 3 dimensions, and we live in a 3-dimensional world. So if you want to find the center of mass of an object that is not a flat object, you can do that as long as, well, if you have a sense of what it looks like. And this density here is the actual density, the density, 3-dimensional density, mass per unit volume, not mass per unit area. So the mass is the triple integral, and this is a variable density. So you might have some object that has more dense on the outside than on the inside or whatever. I know that when I'm 3D printing something, I generally will pick some sort of an infill that will, might be variable density, like the lightning infill. If you're familiar with the whole idea of printing, will be more dense towards the top, less dense at the bottom. So that's a great example of variable density. And the variation occurs up and down, maybe left to right as well, depending on what I'm printing. So anyway, that's what the mass looks like. I'm not going to make you do any like this. I just wanted to mention this because it's, this is why we care about triple integrals. All you're going to have to do for your triple integrals is the basic, like what we've been doing. But just one last thing is that if you wanted to find the average x value, 1 over the mass times this moment about the yz plane, which is x times the density, just like what you would expect, the average y value. So this gives you the center of mass of a three-dimensional object, so that as it rotates through space, like the International Space Station maybe, you'll know what the center, where it's going to rotate around, and maybe be able to figure out how to correct adverse rotations or whatever, if you're on the International Space Station. I know that that's been an issue in the past that they've had to use calculus to figure out, to be honest. Okay, so let's take a peek at the homework to see what it is. I think I've updated it. I like to double check, especially since we have a little bit of time, just to make sure that I did update. So, and the test. I want to talk about that too. So let me pull this over. Here we are. Okay, our beautiful thing here. There, I can see. Okay, so first off, the homework. Where are the assignment? There it is. Assignment list. Let me just double check. Come on. Get rid of this. Go away. Okay, so down, down, down. Keep going, keep going. Yeah, I do have something. Good. So section 15.6, page, and I think I've got it on my iPad, just a sec. 15.6, there it is. Let's just double check. It's numbers 4, 5, 9, and 13. So here, I'll show you what these look like, and then I want to talk just briefly about the exam so that you can know what to do for tomorrow. So 4, 5, 9, and 13. There's 4, you can see pretty straightforward, triple integral. 5, same thing. Number 9, where is number 9? Number 9, they give you the, notice that you're given the solid that you're integrating over in those terms, but you can set up your own. Just let me get it set up for you though, just so you can see. You're going to do a triple integral, and you're going to put the constants on the outside. So I'm going to put x on the outside, so that x there is the outermost integral. The next one, because it only involves x, y equals x, that will be the middle integral, and z is the most complicated, so z goes from x minus y to x plus y. And then put your integrand, just y. So dz, dy, dx is the way I would set that one up. And then let's just take a peek at the last one, make sure it's okay. That one is not okay. Well, no, it's okay. I have compassion. Let's not do that one. I will excise it from the, you could have figured it out. I mean, you can probably figure it out just by looking at it. You're just going to set it up using the functions that are given there. But let's just focus on the basics. When you get to your exam, so, I'll take it off of there. So when you get back to this Moodle page, you'll notice that on the exams help, I've got like 3 things. Wait, where does it say? There it is. It's at the bottom. Why is it the bottom? Well, I'll move it up so it's right before test 3 practice. And this is because I've divided this up differently in the past, and we just happen to be at a different place, and I don't want to have to rewrite this stuff. So when you're studying for test 3, you're going to do some of the problems from the test 3 practice, some of the problems from the test 4 practice, and then make up a Lagrange multiplier problem. And if I have time this afternoon, I will make one up, and I will stick it right there so that you can have something to practice for tomorrow. So I should have time to throw something up here, but just wanted to mention that take some of the stuff from one of these, some of the stuff from the other, and it's only so that I don't have to rewrite all the answers on a new page. So hopefully that explains everything. You're going to be okay. Physics will be all right. Okay, the physics people. All right, if you want to stick around and chat, you can. Otherwise,